Hey everybody, it's Mr. Carr again. Today we're going to be looking at 2.4 day 2, performing number operations with complex numbers. Okay, so our complex numbers are going to be any combination of real and rational numbers. So that's our little comic here. Okay, so solve by using square roots. So when trying to look at this and maybe even trying to graph it, we're looking for our x-intercepts. This might be a little bit tricky at times. In fact, let me pull up a graph real fast here. So if it's 2x squared plus let's add, let me do this. I can just do this by hand. If I do this by square root method, it's actually going to look like this, where I subtract 11. So 2x squared is equal to a negative 48 divided by 2. So x squared equals a negative 24. And then I try to take the square root and look at what happens here. Can't square root a negative. So that means if I'm trying to do this algebraically, or if I do it graphically, you're going to see something else. You're going to see something that looks like this. It's just going to do this right here and never cross. So how do I solve this? What do I do with it? Well, that's where our imaginary numbers come in. So imaginary numbers are based on the idea that if we replace the square root of a negative 1 with the letter I, okay, that's our imaginary unit. I is our imaginary value. Now, here's something to remember. If I, just like our other square root properties, if I take the square root of negative 1 times the square root of negative 1, that is going to just equal to negative 1, just like root 2 times root 2 is 2. Since that is, we're saying here, I times I equals a negative 1, that means I squared equals a negative 1. So when I look at these values here, I want to simplify. Because of the negative, I'm going to treat this like it's the square root of 16 times the square root of a negative 1. Zoom in a little bit here. Okay. Square root of 16 is 4. There we go. Square root of negative 1 is I. So that's what this turns into. Same thing happens with the square root of negative 100. 100 is a perfect square, so that's going to become a 10. But because of the negative there, it's going to be 10i. With 50, first thing I want to do is I'll come over here. I want to break this down. That is 25 times 2. So I take the square root of 5 and the square root of 2 there by itself. So that's going to be 5 radical 2. But again, because of the negative sign inside there, it's going to be 5i radical 2. It's better to put the I right here than it is to put it at the very end, because then it almost looks like it's inside the square root, like the square root of 2i. It might look like this, like that. Some people think that looks like this. So it's just easier to put it with the 5 or put it in front of the square root sign. Okay, so more operations we can do. We can add or subtract our complex numbers. It works just like with our algebra, where we're combining like terms. So since we're doing addition here, I can just do 8 plus 5 is going to give me 13. Negative I and a positive 4i will give me a positive 3i. For the next one, I want to first distribute the negative 2 here. So 7 minus 6i, there'll be a minus 6 and then a plus 12i. So I'm going to combine my real parts here. So 7 and negative 6 combine to 1. Negative 6i and a positive 12i combine to make 6i. The next thing we can do is we can multiply with complex numbers. The thing to remember here is if you ever come up with an I squared, you're going to just automatically replace that with a negative 1. Okay? Excuse me. So if I distribute the 4i, 4 times negative 6 is a negative 24, and that'll be an I then. And 4i times I is a positive 4i squared. Now, like I said, the I squared is automatically a negative 1. So that'll be negative 24i plus 4 times a negative 1, which becomes a negative 4. Now, a lot of times when we write our complex numbers, we write the real part first. So I'm going to swap that order, make it a negative 4 minus 24i. Over here, we're going to just do normal distribution. So 9 times both of those, that's going to give me negative 36. 9 times a 7i is a positive 63i. Negative 2i times a negative 4 is a positive 8i. And then negative 2 times a positive 7 is a negative 14. I squared. As we said before, I squared is the same as negative 1. So this turns into negative 14 times a negative 1. So I can do negative 36 plus we'll go ahead and combine these together. So that's going to give me 71i, and that'll be plus a 14 because this is multiplied by a -1. My last thing to do is combine my two real parts. So that's going to give me a -18 plus 71i. Okay. Last ideas here. Yep, last two examples. So if we're dividing with complex numbers, we can write, when we're trying to write them into standard form. What we want to do for this is kind of like when we rationalize denominators with our square roots. We want to try to get I out of the denominator. So in order to do that, we just need to multiply by something to make it a real number. Like in this case, I. I'm just going to multiply that by an I. But I have to do the same thing to my numerator, which means I am distributing this. So that's going to give me a -5i plus I squared. Underneath, I'm going to have 2 times I squared, which is the same as saying 2 times a -1. So now it can be, let's see here, this will turn into a -1, so it'll be -5i minus 1 over a -2. Since I'm dividing everything by a -2 here, it's basically the same as making them all positive values. And I'm going to rewrite it into our standard form, which probably should write this down. Standard form is always written as a plus bi. So we want to make it into the real part and then the imaginary part. So -1/2 divided by -2 is a positive 1/2. -5 over -2 is a positive 5 over 2i. Okay. So again, oh yeah, here it is again. Our complex numbers are made up of the real number plus the imaginary. So for this case, again, like our rationalizing it, we need to multiply this by its conjugate, which is 1 plus 4i. And I'm going to do that to both the numerator and the denominator. Got a plus sign there. So when I do the numerator, I'm going to distribute the 7. So that's 7 times 1 is 7. 7 times 4i is a 28i. 5i times 1 is 5i. 5i times 4i is a positive 20i squared. Underneath, if you remember about conjugates, what's going to happen with the conjugate is we're going to eliminate that middle term. Well, I'll go ahead and do it here, but you don't have to do this as part of your normal work. So 1 times 1 is 1. 1 times a positive 4i is positive 4i. This will be a -4i, and this is going to be a -16i squared. So the shortcut in this is I don't have to multiply this middle section out. I could skip that because they'll always cancel out if I'm doing this conjugate. So those are going to go away. So what I'm left with here is this will turn into a 28 plus 5 is 33i. This turns into a -20 when it multiplies out. So we're going to combine -20 and 7, gives me a -13 plus 33i. In my denominator, this is going to turn into a -1. So remember, I squared is a -1. And because it's already -16, it turns into a positive 16. So I get 1 plus 16, which is going to give me 16. Since I can't really reduce that, I don't need to separate it, but if you wanted to, you can say that's -13 over 16 plus 33i over 16. And that is it for our operations with imaginary numbers. Hopefully you can see that we're going to use this potentially when we deal with our non-real solutions to our quadratics is the goal. So you can see here, this was a quadratic up here. And that becomes a non-real solution. So that's part of what we're doing today. But for now, we're just making sure we go over these different operations, things like adding and subtracting our like terms. So that's with our complex numbers. We can multiply with our distribution properties. And just remember that if you ever get an I squared, you just replace it with a -1. And then finally, we can also, when we divide out, we want to put them in a standard form. The biggest thing about this is just getting that I away from the denominator makes it a little bit easier to work with. All right. And that's it for today. Take care, everyone.